Welcome to this Vapor Intrusion Basics training module for the Supplemental Vapor Intrusion Guidance document that was released by Cali PA Vapor Intrusion Work Group in February 2023. My name is Steve McMasters. I am the Site Cleanup and Department of Defense Program Unit Lead here at the State Water Resources Control Board Division of Water Quality. So the purpose of this training is to provide you an overview on vapor intrusion basics, as well as vapor intrusion behavior, and some of the nuances and complexity associated with that, as well as provide you a little bit about the terminology that we use in the field for vapor intrusion. All right, let's get into some of the basics on vapor intrusion. First of all, vapor intrusion is the migration of vapor-forming chemicals, or VFCs, in the vapor phase that move from areas of contamination in the subsurface and migrate up into a building. Subslab soil gas is the vapors that exist immediately below a building's foundation, whereas crawl space air, which is not shown on this figure before you, are the vapors that exist within a crawl space for a raised foundation type building. Soil gas, or soil vapor, is the vapors found within a vadose zone due to off-gassing of source areas or contaminated groundwater. Indoor air is the vapors within a building that is subject to air exchange with outdoor air and potentially subsurface air. Ambient air and outdoor air, they're a little bit different, but ambient air is the vapors outside of a building that would be reflective of normal atmospheric concentrations. Whereas an outdoor air is also outside a building, but is collected in proximity to a building and ideally upwind to determine outside source vapors that may be influencing indoor air concentrations. Lastly, preferential pathways and/or vapor conduits are typically utility lines that are prone to transmission of source vapors directly to a building or beneath the building. An example would be a sewer lateral that intersects contaminated groundwater, soil gas, or the source directly. Additionally, high permeable soils or geologic formations and strata may also act as a preferential pathway or conduit if it provides communication between the source soil gas and that building. All right, so within a soil matrix, vapors exist and move through voids between soil particles. As such, soil moisture and water saturation plays a big role in limiting or attenuating vapor migration. Additionally, caution and necessary steps should be conducted prior to collection of indoor air samples, as many household products and items can off-gas and contribute to indoor air concentrations. Examples are gun cleaners, paint, and furniture treated with stain-resistant substances. There are a couple links in the lower left-hand corner of this slide that directs you to both the California Air Resources Board and US EPA for some indoor air source studies for your reference. All right, let's transition now into the vapor behavior and summarize partitioning. I'm not going to go into a lot of detail on partitioning on NAPL, or non-aqueous phase liquid, which has a 4-phase equilibrium partitioning between the NAPL, sorbed, dissolved, and vapor phases, as this would take significant time to discuss all the controlling factors that influence the equilibrium between those phases. Additionally, I'd like to thank Mr. Eric McWayne with the National Environmental Management Academy, who is one of our contractors that routinely provides fate and transport training to our cleanup staff. Thank you, Eric, if you are listening to this, for giving us permission to use this very valuable figure. Okay, so let's get into the two processes for chemicals to enter into the vapor phase. The first is the NAPL to vapor process, which is determined by Raoult's law for mixtures, and then vapor pressure for those pure substances. The second is the dissolve to vapor phase, which is determined by Henry's law. So some of the general things to take away is that the higher the numbers, either for Raoult's law or vapor pressure or Henry's law, it is easier for that chemical to partition into the vapor phase. So vapors move by two processes. First is by advection, where chemicals move within a moving air vapor mass likely caused by differential pressures. The second is by diffusion, where there's thermal movement of chemicals from high to low concentrations. Some general things to take away is that vapor behavior is inherently complex and dynamic. In general, the closer we get to a building's foundation and ground surface, the more variability is observed. These variations are due to natural and man-made controlling factors. Some examples of natural factors include temperature, atmospheric pressure, wind, precipitation, climate, soil type, and soil moisture. Some examples of man-made factors include heating, ventilation, and air conditioning, or HVAC operation, which can cause pressure differences between the building and the subsurface. Heating can also cause something called the stack effect, as the hot air rises within a building, which can draw subsurface vapors into a building. Lastly, building types, their condition, foundation type, and foundation condition can either hinder or enhance vapor migration. To help demonstrate the dynamic nature and vapor behavior, this figure and findings are captured from a case study from the Sun Devil Manor residence overlying a shallow chlorinated hydrocarbon groundwater plume from the Hill Air Force Base in Utah. This residence was part of a multi-year study and monitored for just under a 3-year period under natural conditions. So during this time, there was no mitigation or any remediation during this whole period, nothing to influence vapor behavior. So some of the lessons learned from this case study is that more variability in concentrations is observed the farther from the groundwater source. Subslab soil gas concentrations show between 10 times to 100 times in spatial variation and 10 times in temporal variation. Lastly, indoor air concentrations showed temporal variation up to 1,000 times. To help demonstrate the wide range in temporal variability in indoor air, this graph shows the TCE or trichloroethylene concentrations from 8,000 samples collected at the Sun Devil Manor residence just under that 3-year period under those natural conditions. So data shows significant concentration variation in a single day and also between seasons. Additionally, there was much greater concentration variation during the winter months versus those observed during spring months. So the question I have for you all as you look at this data is, what if this building was sampled for indoor air just once? What conclusion would we draw if we got a 0.54 micrograms per cubic meter value? What conclusions would we draw if we got 54 micrograms per cubic meter, considering our short-term action levels of 2 micrograms per cubic meter for TCE for residential scenarios? All right, let's talk a little bit about the slab capping effect. So buildings, pavement, and other structures can impede ambient air and atmospheric interactions with soil gas. As a result, contaminant vapors can pool below structures. As a general rule, not absolute, but as a general rule, soil gas concentrations found at 10 to 15 feet below the building's foundation and at locations less than 10 feet laterally from that building can be used to estimate subslab soil gas concentrations. That's why those sample locations and depths are recommended as part of the supplemental vapor intrusion guidance. Additionally, we just want to point out that the number and degree of slab capping effect is going to vary depending on site and geologic conditions. Before we get into the next topic, let's discuss what screening levels are and why they are important. So screening levels are a risk-based concentration for contaminants and considered protective for human exposure over a lifetime. They include measurements of how toxic the chemical is and also how long people will be exposed. As such, screening levels are developed for both commercial and residential settings separately. So commercial is based on a 40-hour work week where you have potential exposure for 8 hours a day for 5 days a week, whereas residential levels are based on a 24-hour, 7 days a week scenario. As such, residential screening levels are typically much lower than commercial levels. So as such, an acceptable risk level is set based on a 1 in 1 million chance of cancer and also a non-cancer or acute health effects as well. The last point is that screening levels are generic in nature and calculated without site-specific information. They can be recalculated with site-specific information. Okay, let's get a little bit into attenuation and attenuation factors, as they are an important concept or component of the supplemental vapor intrusion guidance. So attenuation is the reduction of vapor concentrations and impediment of vapor migration due to natural or man-made factors. Attenuation factor is the ratio between measured concentrations between two media. So for this example, I'm using the indoor air to subslab concentrations as part of that ratio. So an attenuation factor for screening, or a screening attenuation factor, is a formula-based approach used to conservatively estimate indoor air concentrations from subslab or soil gas concentrations. In this example, we use the formula-based approach to estimate indoor air concentration using US EPA's default attenuation factor 0.03. So if we have a subslab soil concentration of 1200 micrograms per cubic meter, then we can estimate an indoor air concentration of 36 micrograms per cubic meter. Just remember that using this approach should not be used to predict values, but to estimate a conservative value for screening. So in addition to the generic attenuation factors discussed in the previous slide, building-specific and site-specific attenuation factors can be developed with a robust data set. So building-specific attenuation factors should be based on collection of measured attenuation factors for a given building for a specific time period. Additionally, it's likely that you're going to observe a range of attenuation factors for different sampling events. So for a site-specific attenuation factor, those should be based on collection of measured attenuation factors for site-specific buildings. I did want to exercise caution with these approaches, as vapor will behave differently for every building. Okay, let's talk a little bit about the contaminated groundwater and soil gas relationship. Indoor air concentrations can be estimated from groundwater concentrations. However, this method is not preferred, as a lot of air can be introduced. Additionally, if you're going to use this method, the capillary fringe needs to be considered, as its thickness and degree of contamination varies and creates a lot of uncertainty about the transport of chemicals through it. So the preferred method is get that representative soil gas sample to estimate your indoor air concentration. However, there are scenarios and situations where a soil gas sample cannot be collected, such as a shallow groundwater scenario or very limited access to buildings. So in those situations, you can use a formula-based approach to help you estimate your indoor air concentrations. So if that is necessary, this following formula can be used to estimate your indoor air concentrations, but it needs to be done in steps. The first step is to take your groundwater concentration and convert that into a vapor concentration by multiplying the groundwater concentration by the chemical specific Henry law constant. Then that value needs to be multiplied by 1,000 liters over cubic meter. Then you take that value and you multiply it by a generic groundwater to indoor air attenuation factor, which accounts for the capillary fringe effects. So EPA recommends using 0.001 for generic scenarios, meaning all types of soil types, fine to grain. But if you have really good control of your strata and it is a clay deposit and pretty continuous throughout your site, a 0.0005 generic attenuation factor is appropriate to be used. So that concludes my portion of the training today. We will be hosting live Q&A sessions on this in the near future, and that will be posted. So hopefully you spent some time with the other modules. Mine was just the purpose of getting you familiar with some of the terminology and vapor behavior. We're going to go into a lot more detail on these other modules, so please listen to them. All right, well, thank you for your time today, and I am signing off. Thank you.